Lecture 3B, Model of the Seasons. We're going to take those 6 factors that work in a series of interactions to create the seasons. Now, in this model, we're going to stop the Earth at 4 critical positions in its revolution around the sun. We're going to look at the first day of winter, the first day of spring, the first day of summer, and the first day of fall. What we want to do is make note that these dates occur exactly every 3 months from one another, and they occur on or about the 21st, 22nd, or 23rd. We're going to use the number 21 for each of these 4 dates just for simplicity, so you don't have to worry about memorizing the 22nd or 23rd. And we're going to start with the first day of winter in the Northern Hemisphere, the winter solstice. And let's start with that. Okay, the winter solstice occurs on or about December 21, and that's the first day of winter for us in the Northern Hemisphere. The word solstice comes from the Latin, sol meaning sun, stis status. So what we're referring to is, the status of the sun's rays striking the Earth on this date. All right. What we need to make note of it, during the Earth's orbit on this date, the Northern Hemisphere is tipped away from the sun. So here we've got the equator in the Northern Hemisphere, and here we've got the Earth's polar axis, all right, tilted 23.5 degrees. And so the Northern Hemisphere is going to wind up experiencing winter time. Now the Southern Hemisphere, the opposite is going on. The Southern Hemisphere is tipped towards the sun and is going to be experiencing the first day of summer. Now why is that? Well, the Southern Hemisphere is presenting itself to the sun, all right, more readily, all right, and easier for the sun's rays, or the more direct rays, to strike it. And as a matter of fact, right, the most direct rays of the sun, the subsolar point, is located in the Southern Hemisphere on this date. And this date is marked, right, by the migration of the subsolar point migrating as far south into the Southern Hemisphere as it can possibly go. And that is 23.5 degrees south latitude. Now, this is a very special line of latitude. It's called a sun behavior line, and it's named the Tropic of Capricorn. Where have we seen this number before? That's the tilt of the Earth's polar axis. And so the way the Earth is presenting itself to the sun, this is as far south into the Southern Hemisphere that the most intense vertical direct rays of the sun can go. And so we're going to wind up with, direct rays of the sun at noon, directly overhead, and still very, very high sun angles. And so when you've got high sun angles, you've got maximum heat, maximum heat. And so that's going to create, heating and summer-like conditions. Now, the opposite is true in the Northern Hemisphere. The first day of winter, we're far away from where the subsolar point is, and we're going to have lower sun angles, meaning at noon, the sun is going to be lower and lower and lower in the horizon, and so we're going to have less heating. Now we need to look at the amount of daylight in regards to seasons and heating, and we want to start with the extremes. I want to take a look at another sun behavior line called the Arctic Circle. That is located at 66.5 degrees north latitude. Now, places beyond the Arctic Circle to the North Pole are rotating through the night half of the Earth, all right, through constant night. And this usually occurs for several weeks during December, maybe 4, 5, 6, 7 weeks. It's total darkness. Now, there are towns and cities that are located, at and above the Arctic Circle, in Alaska, in Northern Europe, in Russia. As a matter of fact, the largest city above the Arctic Circle, with a population of 1 million, Murmansk, the people have to deal with total darkness for several weeks. It's very difficult on daily life. So you can imagine how cold it is with no daytime heating. And even here, we've got the latitude of 40 degrees north, kind of the latitude of New York City. And what we're trying to illustrate here is you kind of take a look at the proportion of the amount of day and then proportion of night that the Earth is rotating through. And you can see in the northern hemisphere, here they're illustrating Europe, but even in North America, the proportion of daytime is much shorter than the proportion of night. And so we've got shorter periods of daylight. And so the shorter amount of daytime, well, the less potential heating. And so for us here in Louisiana at 30 degrees north, we usually experience about 10 hours of daylight. Right? I remember being way up here in Aberdeen, Scotland, during Christmas break one year. And you can actually see, I mean, the proportion of daylight was really short. I mean, the sun really wasn't rising until about 10 in the morning. And then by about 2:30, or 3, the sun was set. And so really only a very, very short period of daylight and a long period of night. And so that means less daylight, less potential for heating. So that makes winter. Let's look at the opposite situation where summer is occurring. The Antarctic Circle, another sun behavior line, 66 1/2 degrees south latitude. Now the Earth at this point, right, is rotating through through total daylight, rotating and rotating and rotating. And so Antarctica is experiencing 24 hours of daylight, usually lasting 4, 5, 6, 7 weeks. And so the sun does not set for a long period of time. Now the thing is that the sun is not really high in the sky. We're at the bottom of the Earth. And so the sun is really just making a very, very low sun angle just above the horizon. And so the sun isn't setting, but what it appears to do is just appears to rotate around the horizon continuously for several weeks. But, it appears that the sun is rotating around the horizon. But is it the sun rotating? No, it's the Earth rotating in relation to the sun. So even though they're experiencing, total daylight, they're not really getting much heating since the sun is very, very low in the sky. But then again, you can kind of take a look, at the proportion of daylight versus the proportion of nighttime. And here's Australia. I mean, they're experiencing the first day of summer. And in December, I mean, at Christmas time, it's very, very hot in Sydney, at 30 degrees south latitude. It's usually in the 90s at Christmas time. And of course, one of the big reasons is, high sun angles and really long period of daylight. And the longer the amount of day, the greater heating. All right. Here's a nice picture of a very, very high latitude location in wintertime. And the example of the sun at its zenith, at its highest point in the sky at noon. And the sun is only making a very, very low sun angle above the horizon. And you're not going to get much heating from that. And so the sun at its zenith at noon is only a few degrees above the horizon in winter at very, very high latitude locations. All right, so let's now continue the Earth in its orbit around the sun, and we're going to have the 3 months of winter in the northern hemisphere. So we're going to finish off December, then we're going to have January, February, March, and then on or about March 21, we're going to have another critical date. Now, during these 3 months, the Earth is presenting itself as slightly different every single day. And so the subsolar point, the most direct, intense vertical rays, wind up moving a little bit every day. And the subsolar point is going to be moving from its farthest location in the southern hemisphere northward during the months of winter. And on the day that the subsolar point has migrated to the equator, marks the first day of spring. And it's called the spring equinox for us in the northern hemisphere. Let's take a look at the details of this situation. All right, the vernal equinox, vernal is Latin meaning spring or youthful, and it's the first day of spring for us in the northern hemisphere. It occurs on or about March 21. Now for the southern hemisphere, it's the opposite. I mean, we just had summer in the southern hemisphere, so this is going to mark the first day of fall for them. But we're just going to think of the northern hemisphere. I mean, you're just going to have to think about that. And all right, now as I mentioned, all right, during those 3 months of winter time for us in the northern hemisphere, the subsolar point has been migrating day by day. And the first day of spring is marked when the subsolar point has reached the equator. And here we've got it illustrated here. All right, so the sun's most direct, intense vertical rays, making a 90-degree angle, has reached the equator. All right. Now, the important thing about this day is that all places on Earth on this day are experiencing equal periods of day and night. All places, even above the Arctic and Antarctic circles. Every place is receiving equal periods of day and night, 12 hours each. And indeed, the word equinox, again, is Latin, equa, meaning equal, nox, meaning night. All right. Now, what was going on during those 3 months of winter time? Not only was the subsolar point migrating because the Earth was presenting itself at slightly different angles every day, all right? The other thing, too, is the circle of illumination, all right, is also moving. And what we need to show you here is that this is it. We're going back to the model diagram. And what we're doing in this diagram is we're eliminating the tilt of the Earth's polar axis, just to show you the equality that's going on in terms of day and night. But in fact, the tilt of the Earth's polar axis is still there. That's why I've made this little cutout. What we're doing is looking at a side view over here. And what you can see is now the circle of illumination is lining right up with the poles. And that's what we're illustrating here. All right. And so during those 3 months of winter time, let's go back to, areas above the Arctic Circle. So for maybe 6 weeks, it was total darkness. And then one day the sun came out for maybe about 10 minutes and then set. And then the next day the sun came out longer, for 20 minutes. And then an hour, all right, 2 hours, 3 hours, 4 hours, 5 hours. And then finally, after 3 months, right, of the Earth's orbit, we've reached this date where the sun is now out above the Arctic Circle for 12 hours, all right, just like every other place. And the same thing with the Antarctic Circle. One day, after about 6 weeks, the sun set for a few minutes, and it set longer and longer and longer, and then until we've reached 3 months where the sun is now set for 12 hours, and then we have 12 hours of daylight. And it's all because everything is equal. I mean, the subsolar point is, at the midpoint between the poles, and everything is in equality. All right. Now let's move on through the 3 months of spring. And so we're going to finish off March. We're going to move into April, May, into June. And on or about June 21, we're going to have another critical date. It's going to be the first day of summer for us in the Northern Hemisphere. Now, during these 3 months of spring in the Northern Hemisphere, the subsolar point is migrating, right? And it's migrating northward. And it all has to do with the way, again, that the Earth is presenting itself during these 3 months to the sun. And it's all related to the tilt of the Earth's polar axis. Because now we're in the opposite location in its orbit from where we began. And now you can see that the Northern Hemisphere is tipped towards the sun. And so what's been going on, right, is the subsolar point has been moving into the Northern Hemisphere day by day. And so from the equator, all right, the subsolar point day by day has been slowly moving into the Northern Hemisphere. And on the day that it reaches as far north into the Northern Hemisphere that it can go, marks the first day of summer. All right, it's called the summer solstice for us in the Northern Hemisphere. It occurs on or about June 21. And now, 6 months from where we began, the Northern Hemisphere is tipped towards the sun, and we're going to be experiencing the first day of summer. The Southern Hemisphere is tipped away from the sun, and they're going to be experiencing the first day of winter. All right, what marks this date, all right, is when the subsolar point has migrated as far north, all right, as it can possibly go into the Northern Hemisphere, and it's reached 23.5 degrees north latitude. And so the subsolar point is at a special line of latitude, and we name it. It's called the Tropic of Cancer. All right. And so now we can see that the northern hemisphere is getting the most intense direct vertical rays of the sun, high sun angles, right, making greater heating for summertime. And the southern hemisphere is now far away from where the direct rays are, lower sun angles at noon, creating, less heating. And again, we've got to kind of take a look at the amount of daylight in each hemisphere. Now, the opposite is going on in the northern hemisphere. And here we've actually, in this diagram, we've actually got the Arctic Circle illustrated at 66½ degrees north latitude. And now, let's add rotation around the tilted polar axis. And now, very, very high latitude locations are experiencing several weeks of total daylight. Usually about 6 weeks of total daylight. And so the sun is just constantly out as the Earth is just rotating through the day half of the Earth. And so from where we just were with spring, remember areas above the Arctic Circle, just like all places on Earth, are experiencing 12 hours of day. Well, after the first day of spring, the sun just kept on staying out longer. 13 hours, 14, 15, until we reach this date on June 21, where it's 24 hours. All right, and then the opposite is going on. And here we've got the Antarctic Circle, 66½ degrees south latitude, and now the Earth is rotating through the night half of the Earth because, again, the polar axis and the circle of illumination are not matching up on this date. And for about, usually about 6 weeks, Antarctica is experiencing, total darkness. And you can imagine, how cold it is then. All right. Okay. So now we're going to be experiencing the 3 months of summer for us in the northern hemisphere. And so we're going to continue the Earth in its orbit through the end of June, July, August, September, right? And on or about September 21st, we're going to say, right, the Earth has reached another critical position. And what has happened, right, is during those 3 months of summer, the way the Earth is presenting itself with its tilt of the Earth's axis, right, the subsolar point is going to be migrating now southward, all right, from its farthest northern location, the Tropic of Cancer. Day by day, it's migrating southward. And on the day the subsolar point reaches the equator, marks the first day of fall for us in the northern hemisphere. So we're going to have another equinox situation. All right, so the situation is going to be the exact same as the first day of spring. And so we call it the autumnal equinox, or the first day of fall for us in the northern hemisphere. It occurs on or about, we'll say, September 21. And as I said, the northern hemisphere is experiencing the first day of fall. And then obviously the southern hemisphere is experiencing the first day of spring. All right, now the subsolar point has moved back to, its midpoint between the poles. And here we're showing the sun's rays, the subsolar point, directly overhead at the equator. And again, the situation is going to be equinox. All places on Earth on this equinox situation are experiencing 12 hours of day and 12 hours of night. And again, they've eliminated the tilt of the Earth's polar axis in this diagram. It's still there. It's just the view that we're taking, and we're looking at a side view. And you can actually see the circle of illumination is actually matching up with the North Pole, and areas above the Arctic Circle are experiencing equal periods of night and day. Right. So let's finish off the year, and we're going to have now the 3 months of autumn. And so the Earth is now going to be orbiting through September, October, November, and December. And during these 3 months of fall in the northern hemisphere, the way the Earth is presenting itself to the sun, the subsolar point is going to be migrating from the equator southward. And on the day the subsolar point has moved as far south in the southern hemisphere as it can go, marks the first day of winter for us. That's where we began in our lecture, 23½ degrees south latitude. I also want to, just kind of take a moment now that we finished the 4 critical positions of Earth and Sun, just kind of where we are, in late January, in our class. And so we're kind of right here, about a month from the first day of winter on December 21. And so we're kind of at the end of January. So we're about here, all right? And so then we've got, February and March to go. We still have 2 more months to go. And, what I want you to kind of notice, in your daily life is that the days are getting longer. Daylight is getting longer. As the subsolar point now is getting just a little bit closer to us, at the equator. And we're going to have kind of an intermediate season where we don't have those great extremes, of tilt. And so, right now, with the sun is rising, about 7 a.m. and sun setting about 5:30. And what's going to wind up happening is, what you're going to be noticing, sunrise is going to be getting earlier and earlier and earlier, and sunset is going to be getting later and later and later. And so the days are going to be longer, getting longer and longer. And so we're going from about 10 hours here in Thibodaux of daylight on the first day of winter to, of course, 12 hours. And so when you are adding 2 hours of daylight, you're going to get more heating. And so it's going to be kind of, an intermediate season, as opposed to, where you're getting the most intense rays of the sun, creating summer or hot. So we've got our intermediate and then our extremes. All right. Okay, that's the model. What I want to do is take a look at a very interesting graph that plots the migration of the subsolar point during the year. And in this graph, since we're plotting the migration of the subsolar point, we've got a graph showing the tropics. And so here we've got the equator, and here we've got 5-degree increments of latitude, and then here's the Tropic of Cancer, 23.5 degrees north. All right. Now, don't worry about these minus signs, but this is basically, the southern hemisphere, and 5 degrees and 10 degrees south latitude. And so we're going to the Tropic of Capricorn here, 23.5 degrees south latitude. And so this is where we began in the model. The first day of winter, and that's when the subsolar point is at 23.5 degrees south, all right? And then here we are, actually this is where we are today, well, I kind of want to point that out. We're at the end of January, and so can you tell me, where is the subsolar point today? Right? Where is it about? Okay. It's definitely, still in the southern hemisphere. It's probably about 20 or 21 or 22 degrees south latitude. And where is it heading? I mean, we're in winter time, heading towards spring, where it's going to start to get warmer. And why is it getting warmer? Because the subsolar point over the next 2 months is getting a little bit closer to us. All right. And so then we're going to have our first day of spring. Right, intermediate season, all right, temperature-wise, and then, right, then we're going to have the months of spring, all right, April, May, all right, and then into June, and the subsolar point has reached as far north as it can go. 23.5 degrees north latitude marks the first day of summer. All right, and so we're going to have really, hot temperatures for us in Thibodaux because the subsolar point is really pretty close to us, okay? Where are we located? We are located 30 degrees north latitude, all right? And so, no, we don't get the subsolar point, in Thibodaux, but let me tell you, our sun angle is pretty high, all right, on the first day of summer. And so we're going to have pretty high sun angles. Not 90 degrees, but something like 84 degrees is what it's going to be. About 84 degrees on the first day of summer. That's still a pretty high sun angle and pretty intense heating. And then we're going to have the months of summertime, and then the subsolar point, day by day, during July, August, and September, are moving back to the equator. And you have the first day of autumn for us, and everything, is kind of intermediate. And then during the months of autumn, it starts to get colder, usually October, November, and that's because the subsolar point, those most intense vertical rays, are moving farther away from us, all right, until we reach winter, all right, our coldest season for us in the northern hemisphere. All right, and so this is showing the migration of the subsolar point during the year within the tropics. And so obviously the subsolar point never reaches us in Louisiana since we're at 30 degrees. All right, I want to make a conclusion about the seasons. All right, heating. Why is it hot in summer? Why is it cold in wintertime? And why we have those intermediate seasons of spring and fall. And really, what I've tried to talk to you about at those 4 critical positions are these 2 things. The sun angle. All right. All right, here's a diagram kind of illustrating sun angle using a flashlight. And you can actually do this, all right? Take a flashlight in a dark room at night and have it directly vertical, making a 90-degree angle with the floor. And when you've got, vertical rays, very, very high sun angles like the subsolar point, you're going to get heat concentrated. You're going to have the greatest heating that is possible. And that's because they're kind of imagining 1 unit of sun's rays, and it's actually striking the earth over that exact same 1 unit. And so you're going to have the most intense heating, all right? And then you've got progressively lower sun angles when it's winter time. Here, let's kind of go to a winter or high latitude location with a low sun angle. And here they're just having a sun at noon, only about 30 degrees off the horizon. And that would be almost kind of winter time for us. I think at winter time we're at about 36 degrees on the first day of winter. So we have really low sun angles. And so what winds up happening is that 1 unit of heat energy, all right, because of the angle is now going to wind up striking the surface over twice the area. So that amount of heat is lessened 2 times. And so that's why when you have low sun angles, you have less heating. And just do that. I mean, with the flashlight, you'll see, really intense, heating, intense bright light where the subsolar point is, all right? And then tilt your flashlight on the dark floor, and you will see it spread over a much larger area, and the intensity of that light is greatly lessened. So you're going to have less heating. All right, so sun angle definitely determines hot and cold. Right. Summer. And then, of course, the amount of daylight was something else that we were talking about. Now, as we can make note of, now during the year, the amount of daylight can range from 0, and where you have absolutely no heating for a long period of time, and you can imagine how cold it gets when you don't have any heating, to 24 hours, right? And so, I mean, obviously during the summer months, when you have long periods of daylight, maybe 14, 15, or 16-hour days, the longer the daylight, I mean, the longer or the greater potential for heating. And then the opposite. I mean, if you've got periods of short daytime, I mean, the potential for the sun being out is less, and you're going to have less heating. And so those are really the 2 factors that create, the seasons, summer and fall. I mean, sun angle and the amount of daylight. Okay. And this is kind of another conclusion. I kind of really like this diagram. And this is what we're talking about, the sun at noon. All right, the sun at noon. And they're actually illustrating almost a latitude location for where we are at 30 degrees or 30 or 40 degrees north or south latitude. And so we say that, the sun is makes its way, above the horizon at sunrise at the circle of illumination, and appears to rise during the day. But of course, we're rotating to the noon meridian, and then reaches its zenith and then sets. Okay. Now, let me just ask you a question: is the subsolar point illustrated in this diagram? No, the subsolar point is not illustrated. If it was, the sun would be directly overhead the sky. All right, so this is kind of a nice diagram for us. Okay, and so during the summer months, like I said, our sun angle is about 84 degrees on the first day of summer, and so it's a high sun angle, and you're going to get pretty good heating. All right, pretty intense heating because we have high sun angle. And then in winter time, since the subsolar point is really far away from us in the southern hemisphere, our sun angle is going to be quite low, something like 34 or so degrees, maybe 36 degrees, but still quite a low sun angle, right? And so those sun rays are going to be spread over a much wider area and at lessened in intensity. Okay, and so anyways, this is the conclusion for summer and winter time in terms of sun angles and the amount of daylight. All right, that really is as simple as that. Okay. All right, so you absolutely need to know your sun behavior lines, okay? On those 4 critical dates, where is the subsolar point? You need to know exactly where they are. You need to know the latitude, location, and the name, okay, of that sun behavior line. And here they are right here. I mean, so you need to know 23.5 degrees, and you need to know 66.5 degrees. Now, if you get confused, all you got to do is add 23.5 and 66.5, and that's going to equal 90. All right, it's got to equal 90. But anyways, you need to know your sun behavior lines on those 4 critical dates. And you also need to know the amount of daylight and darkness, okay, in each hemisphere. And it kind of makes sense. I mean, if it's summertime, we're going to have a lot of day, and the Arctic Circle is going to have total daylight. And as a matter of fact, I mean, I'm asking, what day is shown in this diagram. And of course, the vertical ray is representing the subsolar point. And so this is the first day of summer, June 21 for us in the Northern Hemisphere. That's illustrated here, okay? And so you need to know the amount of daylight and darkness and what's going on beyond the Arctic Circle on this day, too. All right, and here's just another example, okay? Again, showing the names of those sun behavior lines, but you also need to know the numbers. And of course, the vertical ray means the subsolar point. It's at the equator. Well, it's one of 2 days. It's either the first day of spring or the first day of fall, where every place on Earth is intermediate, okay? 12 hours of day and 12 hours of night. End lecture.